All right. Let's see. In Module 3, we learned about star birth. Back in Module 2, we learned about stellar evolution from star birth through, well, there we went through the horizontal branch, which is getting pretty close to star death. There's a little bit more to the story, and we'll hit that in this video. And then you have star death, which can take a variety of different forms. Now, I love this picture. This picture kind of summarizes everything. So we'll start here and then we'll dig in deeper. In the center, we have a cloud of gas, and that's where the stars form. And you can form low mass stars, which have a particular evolutionary path. That's the one on the left, or high mass stars, and that's the evolutionary path on the right. Now, low mass stars, those are stars like our sun. Our sun's considered a low mass star, goes through its lifetime, becomes a red giant. As we'll see in this video, becomes a red supergiant. And then it will end its life in a planetary nebula, throwing off its outer layers. And the core that's left behind is something we call a white dwarf. They're about the size of Earth. Now, on the right-hand side, that's high mass star formation, talking about stars that are starting with a solar mass of 12 or greater. Now, by the time they die, they have a little bit less because they lose a lot of their mass in stellar winds. These are high mass stars. They form, giant stars as well. And the end product is a supernova explosion. And this can give you two different compact remnants, a neutron star or a black hole. Okay. Now, let's talk about low mass star death. Here we go. Okay. So here's an HR diagram. We're quite familiar with these from Module 2. This one's fairly evolved, as you hopefully can tell just by looking at it. And let me just start by reviewing briefly what we learned back then about stellar evolution, so I can take you through the whole story. Stars start, well, they start as clouds that collapse, and eventually they're fusing in their cores. And that's when we consider the star actually live. It's actually turned on. It's no longer a protostar, but the real deal. And it starts its life on the main sequence. And we can see the low mass end of the main sequence here. In this particular HR diagram, the high mass stars have already evolved off. But stars start on the main sequence, and they are in what we call hydrostatic equilibrium. This is a balance between pressure and gravity. So at the core, they're fusing hydrogen into helium. Main sequence stars are, colloquially, we say burning, but it's not chemical burning, it's actually fusion. But I like the colloquial terminology. So you're burning hydrogen and producing helium and energy. And that energy is creating pressure that's pushing the star outwards. Gravity's pulling it inwards, and they're in balance. That's the equilibrium, hydrostatic equilibrium. And stars spend most of their life, the sun will spend like 10 billion years on the main sequence. It's about halfway through now. And here's a star at the beginning of its life. It's mostly hydrogen, a little bit of helium. And these are the abundances given to us after the Big Bang. For the first, from about 3 minutes till about 20 minutes, the temperature everywhere in the universe was just right for hydrogen to fuse into helium. It was essentially like the inside of a star everywhere. They're so dense and so hot. Just for that short period, then the universe expanded and the densities dropped and this stopped. But during that period of time, we produced a fair amount of helium and some other minor things, small amounts of deuterium and lithium and a tad bit of beryllium, but that's it. Everything else has been made since then in the bellies of massive stars. Anyway, most stars start out like this. Even if it has the other elements, they're very small amounts. It's primarily hydrogen, helium. And because the temperature in the center, you're burning through the hydrogen. Here, our sun is kind of like this. And eventually, you'll be out of hydrogen in the center. You're still burning it for some distance from the center out till where it's not hot enough, not dense enough to do the fusion. And out here, you have just regular hydrogen. Okay. But this marks the end of a star's time on the life sequence, on the main sequence, the end of their lifetime on the main sequence, because in the core you have non-burning helium ash. Again, ash is a colloquial term. Just means this was the residue from the fusion, and it's not burning. It's not hot enough. Around that, you have a hydrogen-burning shell, a shell that's still burning hydrogen, and out there, out beyond that, you have the non-burning hydrogen, etc. Okay. Now, this core, as we talked about before, there's a video on all this before, the core is shrinking slowly. It's hot and dense, so it's not going to just collapse down. It is shrinking, and as it does so, it heats up. It's converting, if you recall, gravitational potential energy into kinetic energy of the collapse, and as things bump into each other, that's friction, and it's converted into heat. So as the core shrinks, it heats up. And it heats up the surrounding hydrogen-burning shell. And at that higher temperature, the reaction rate goes way up. So it produces a lot of energy, some going into the core, heating it up faster, and a lot of it going into the outer layers, which poof them up, and they expand, and the very outermost parts cool because they've been spread out. And this is this mirror that I talked about before. The stars, what's going on in the core and the outer layers, it's always opposite. The core is shrinking, the outer layers are expanding because of the mirror effect of the hydrogen burning shell. Okay, so they move up here on the red giant branch. Size is kind of along this diagonal from the lower left to the upper right, you're increasing size. So the stars move off the main sequence, they get bigger, and the outer shell gets cooler because of that expansion. So they end up here, red giant stars. And they work their way up until the core gets hot enough that it can actually fuse helium in the triple alpha reaction. We talked about this before. A two-step process, but in summary, 3 helium nuclei go in. We call those alpha particles, hence the name triple alpha, and carbon comes out and energy. And so now, what was a non-burning helium ash core has ignited, and it expands because it's hot and expands, and that stretches out the surrounding hydrogen-burning shell. So its reaction rate goes way down, and so it's no longer producing energy that supports the outer layers, and they contract because of the contraction, the heat. So you end up down here, they move slightly smaller in size with the outer layers getting hotter. Again, the mirror effect. The core is growing, the outer layers are shrinking, heating up. And you end up on the horizontal branch, and where you end up depends upon the mass of the star. Lower mass stuff to the left, higher mass stuff to the right. Okay. And this is where we left off last time. We are once again in hydrostatic equilibrium. The core is producing energy that pushes against gravity, so the star is stable. But it's much shorter lived than the time on the main sequence. Main sequence, you're there for a long time, then you go out of equilibrium, go through that dance we just described, and you end up here. And it's a way station before ultimate death, a little reprieve. But it only lasts as long as you have helium burning in the core. Eventually, you burn through the helium in the core, leaving you with a carbon ash core. Same thing happens again. It's non-burning, starts to contract and heat up. That heat heats up the surrounding hydrogen and helium burning shells. That boosts the reaction rate, which inflates the rest of the star, and you become not just a red giant, but a red supergiant. You can see there are a few stars up here above the horizontal branch. And these are stars that have gone through this process. They're no longer burning helium in the core. The core is contracting, the outer layers are expanding, getting bigger and hotter. And where you end up depends upon where you start on the horizontal branch, but there's a smattering of stars up here. Not very many. You don't spend a lot of time here. You're at the end of your stellar life. It's like if you go outside, downtown, and watch people. Uh, you'll find some 100-year-olds if you watch long enough, but not many of them because you don't last long in that stage. They're near the end of their life, low, small fraction of the population, and then they're gone. And that's what's happening here. So let's talk about these stars up in the asymptotic branch. What happens to them? Well, it's all driven by the helium burning shell. Unlike the hydrogen burning shell, which is very stable, the helium burning shell is not. It's going through phase changes from normal gas, and normal gas, if you heat it, it expands. But there's also a state of matter called degenerate gas, degenerate material. It's what holds up white dwarfs and neutron stars, etc. And it behaves very differently to heat. You can heat it, it doesn't really expand. And the helium burning shell is going in and out of degeneracy, going back and forth between being a degenerate gas and a regular gas. And this makes the outer layers of the star unstable. They start to oscillate wildly. Well, on a timescale of like 1,000,000 years, right? This is not like over the course of a couple hours or days. Over the course of 1,000,000 years, the stars are getting bigger, smaller, bigger, smaller, but the amplitude you can see is increasing. It's getting bigger and bigger. Now, every time you have an oscillation, you lose a little bit of material, and we call these structures protoplanetary nebulae. Okay. And in Module 5A, that's one of the 4 things that you can image. They're kind of small and hard to image. But eventually, these oscillations get so big that the outer layers are expanding at the escape speed. And so they escape. They just lift off. It's not an explosion. A planetary nebula is not an explosion. The outer layers just lift off because they're expanding fast enough that the gravity can't hold them. And you end up with this expanding shell of gas that we call a planetary nebula and a white dwarf in the center, the core of the star. So a sun-like star, it will leave behind a core that's about 6/10 of a solar mass. And it's only about the size of the Earth. It's really dense. Since it's so small, it's very hot. It's emitting a lot of energy per unit area, but it's so small, it doesn't have a lot of surface area. So these kind of faint, and they'll be blue in color. If you make a true color image, a natural color image, they'll be blue in color because they're hot. But then you have the expanding gas around it. Now, this is a very boring looking planetary nebula. Here's another where they've used different colors for different types of gas. This appears to be a Hubble palette where the O3 is blue and the H alpha is red, green, and the S2 is red. And like a planetary nebula, you have ionized gas. You have gas that's been expelled, but that white dwarf is hot. It's ionizing it. And so these are going to be great narrowband targets. Now, that's the second thing you can observe in Module 5 is a planetary nebula, and you might see the white dwarf as well. Let's look at some more of these. They could be really weird in shape. What's making it expand like this? Well, there's dense material around its equatorial plane. So as the star is expanding, the easiest way for gas to escape is through the poles. During the protoplanetary phase, it can get into this kind of oscillatory structure where it leaves a density of gas around the middle, so it expands more on the poles. And then on the next oscillation, you have a higher density on the poles, so it expands in the equatorial plane. And then eventually you have the final expansion, you lose the material, but it can be constricted by gas one way or another. And so planetary nebulae can be quite interesting and intricate, such as this one right here, or this one. Okay. Now, Here's just another example. We saw this one back when we did Module 2. I probably used this as an example. It's a star cluster. And in your star clusters, your open clusters, you may have caught a stray planetary nebula. You may want to go back and look at that data. This one is actually unrelated. It's in the foreground. It's 3 times closer than the star cluster. But you have this expanding shell of gas, and we now know that the red, that's H alpha primarily, and the green here, that's O3. And in the middle, you see that blue star, that's the white dwarf. It's blue because it's very hot, but it's not very bright because it doesn't have much surface area to emit light through. Okay. So that's low mass star death. Let's talk about high mass star death. Now, on this HR diagram, you don't even see any high mass stars. This one's fairly evolved. All the high mass stars are gone. As we said before, they live hard and die young. They have a lot more fuel, but they burn it even more quickly. Let's talk about what they'll look like in your imagery first. So high mass stars, before they die, they have very strong stellar winds, much more stronger than our sun. Our sun has a stellar wind, but the more massive stars, they're bigger and they have a hard time holding on to the gas at their outermost extent, and so they lose a lot of gas. And so you can actually blow bubbles and image these. Here's one, and it's a Hubble palette. So the blue, it's emitting a lot of O3 in this bubble. It's a bubble that's been blown by the massive star. So wind-blown bubbles, the stars are called Wolf-Rayet stars. That's another thing you can image in Module 5A. Now, what's going on with the insides, these massive stars? They're more massive. There's more gravity, more pressure and temperature at the core. So you keep burning. It's not just hydrogen and helium and carbon, but you make oxygen, neon, magnesium, silicon, all the way to iron. Each of these were like adding an alpha particle. That's 2 protons. There are other interactions, reactions that give you the intermediate elements. Their abundances are lower. If you check out the abundances of this stuff in the universe, every other element has a higher abundance than the ones with odd numbers of protons. Anyway, you create this onion skin layer, though sometimes there's mixing under different circumstances. And eventually get to iron at the core. And iron is a very special element. You can't get any energy out of it through fusion or fission. So here's a chart from nuclear physics or nuclear chemistry. It's the amount of mass per nuclear particle. And so, if a nucleon has 10, if a nucleus has 10 nucleons, take the mass of the nucleus and divide by 10. What's the average mass per particle? And you might think it's all kind of the same. Protons all weigh the same, neutrons all the way the same, but in combination, they don't. For example, if you take hydrogen and convert it into helium, the helium nucleus will have a lower mass than all of the components that went into it. Some mass is being converted into energy. That's the source of the fusion energy. So coming down here, you're turning mass into energy until you get to iron. On the other side, that's fission. That's what we use in our fission reactors. We dig up uranium, plutonium, and these things break apart on some natural timescale. And particularly if you put them in close proximity, they can create runaway reactions. That's what our fission bombs do. But in nuclear power plants, we control this. Anyway, uranium, take uranium, breaks apart into 2 parts. The 2 parts have less mass. Added together, they have less mass than the original particle. Mass has been created into energy. You get energy. That's fission energy. Well, they're both going like this. There has to be a point in the middle. That's iron. And most stable element. And you can't get energy out of it. And so once you make that iron core, that's the end. It takes about a day to build up that iron core and about a second for the rest of the story. Happens really quick. So it collapses because it's not producing energy. It collapses. It has a lot of gravity. There's a lot of mass there. And you have the whole rest of the star with its weight coming down on it. So that star, that core, that iron core is squeezed. It's really kind of sad. You went through all these stages to build up complicated elements, and a lot of them will make it out in the explosion to come. In the core, they're all broken apart, right back down to neutrons, protons, and electrons. And the squeezing is so much, the protons and electrons get squeezed together into neutrons. So you end up with a giant ball of neutrons, about 20 kilometers across, size of a city. But the mass of this thing is like 1.4 times the mass of our sun, up to maybe about 3. Talk about that in a second. But you get this giant ball of neutrons. You can view it either nuclear, through the lens of nuclear physics or nuclear chemistry, or through the lens of astrophysics. Take a nuclear approach, that's a nucleus. It's a nucleus with 10 to the 57 nucleons. You got to add an element to the periodic table, neutronium. This is almost pure neutrons, though there are some protons and electrons mixed in. They come to an equilibrium state, mostly neutrons. But it's not held together by the strong nuclear force. It's held together by gravity. So we tend not to think of this as a nucleus, but as a star. Stars are held together by gravity. We call it a neutron star. Okay, and that's the core. Now, meanwhile, the rest of the star is collapsing down on it. It squeezes it. It overcompresses it. And neutron star material is fairly rigid. It gets overcompressed and it rebounds violently, throwing off all the star above it in a supernova. This is what a supernova is. And supernovae, if it occurs in our galaxy, happens once every couple hundred years, you can see it during the day. It's so, unless it's behind a lot of dust, you can see it during the day. This is the Crab Nebula. Went off the supernova. It's called supernova 1054. Went off in the year 1054, and it was visible during the day for weeks. And it's been recorded historically. And here it is today. It's no longer what we call a supernova, but a remnant, the expanding shell of gas. But in there, there's a neutron star. You can't see it in this image, but if you look in the radio, as we'll learn, you can see it. Okay. And these shells, these supernova remnants, they continue to expand and get really broad and diffuse, and they mix back in with the surrounding gas, creating new clouds that will form new stars. The only difference is that gas is now enriched. It has all those elements, other than that iron core, but it has all those elements that were made and other elements that were made, heavy elements, very heavy elements that were made in the explosion. Okay. And the next generation of stars will have more what astronomers call metals, but heavy elements. And the next will have more, and next will have more. And eventually you have enough to make planets and people and stuff. You've been through, the stuff you're made of has been through 50 supernova explosions to make it. Stuff you're made of did not come from the Big Bang. It came from this process. So that's high mass star formation, and you have two remnants, the neutron stars and the black holes. And we'll come back to the neutron stars in Module 5B, but also a little bit in 5C. And the black holes, you got a taste of them in Module 4, supermassive black holes at the cores of other galaxies. And we'll see more of those in Module 7. But we'll also come back and talk about smaller solar mass black holes, or at least tens of solar masses, in Module 5C, where we'll talk about gravitational wave physics. Okay. Oh, and the difference between them is if that core, to form a neutron star, it needs to be at least about 1.4 solar masses. Most of them are there. They can get up to over 2. We've measured some over 2. And once they get up to about 3, we don't know exactly where the boundary is, somewhere around 3. They're so massive that they'll just collapse down to black holes. So that's the difference between whether you get a neutron star or a black hole. It's just the mass of the core, which depends on the original mass of the star. The star is above 25, 30 solar masses. you'll end up with a black hole. Very rare. Okay, we'll stop this video there.